we are going to discuss about finding the maximum and minimum of a function who has two variables in it. Means if a function f of x comma y has two variables, then how to find its maximum and minimum? First, we have to know the partial differentiation of a function. Then we can find the maximum and minimum of these type of functions. First, let us consider a function z, which is an function of x and y. Function of x and y. When we are finding the differentiation of an z with respect to x, we have to keep y as constant, and we have to differentiate the whole function. If we are finding dz by dy, then we have to keep x as constant and we have to differentiate with respect to y. This is known as partial differential equation. If you are finding d square z by dx dy, then we will make it as d by dx of dz dy. First we will find the differentiation with respect to y, then we will treat y terms as constant, and then we will again differentiate with respect to x. That is the procedure. I hope you guys got a basic idea what is meant by partial differential equation. Then now just look at the problems what we have. Just consider a function z equal to x cube plus y cube minus 3ax. That means it's a function of its variable of x, variable of y, and it contains both x and y. Now I find dz by dx. Now I have to keep y as constant, y constant. So just consider if it's y is constant. If y is constant, then it's going to be 0. And differentiation of x cube with respect to x, 3x square. And we are keeping y as constant. So take out 3ay outside. And differentiation of x with respect to dx is 1. That's what we wrote. Same with respect to y. Same with respect to y. We are keeping x as constant. So constant dy of constant equal to 0. And we are differentiating y cube with respect to dy. We are going to get 3y square, and we are keeping 3ax as constant, and we are differentiating y with respect to dy. We are going to get 1. So 3y square minus 3ax. If you want to find again d square z by dx square, then we are going to differentiate again what we call d by dx of, already we differentiate d by dz of d of dx. We are differentiating the outcome that we got in first differentiation with respect to dx again. That's what I'm doing. D by dx of this thing here. And this whole thing is constant now, as y is not considered as a variable with respect to partial differentiation with respect to x, then it's going to be 0. Differentiation of 3x square is 6x. And differentiation of, same thing. I'm going to differentiate here. D square z by dy square. I'm partially differentiating the outcome with respect to dy. Its whole thing is constant, so it's going to be 0. D by dy of 3y square equal to 6y. Now we have to find d square z by dou square z by dou x dou y equal to, first consider dou z by dou y into dou x, or you can take it as also, it is also possible, dou z by dou x. Both things are same, both are same. It's called change of variables. It's a basic property of a differentiation. We can change the differentiating variable. If we have differentiation with respect to so many variables, then we can choose the appropriate variable first, then another variable next. I'm finding, just see, now I'm differentiating the output of dz by dx with respect to dou y. Just consider it's the output of this thing, and I'm differentiating with respect to dou y. And this whole thing is constant, and it's going to be 0. 3ay with respect to, when we differentiate with respect to dou y, it's going to be minus 3a. See, same thing, came out. We observed that dou square z by dou y dou x equal to dou square z by, that's what I said. Now just take t as a function of p and u. Just consider an arbitrary function t of p and u. Now if you want to find dt, that means absolute differentiation of a function. Dou t in the sense partial differentiation, dt in the sense absolute differentiation. Now we will differentiate the t with respect to p. Dou t by dou p into dp. As we are treating u as constant and separating the variables, I mean taking p as one variable and taking u as variable, and that means I can take it t of p comma u is equal to capital P of p into u of u. I have separated the variables. Now I am considering it as p as one different function and u as some different function. So I differentiated the t with respect to p first, and I took the absolute differentiation of p plus dou t by dou u into du. That's what we get. Same thing, if you are going to have a t of function of p and phi, this is what we have to do. First, with respect to partially differentiating with respect to p, then partially differentiating with respect to phi.